Yeah, so I'd like to talk about the machine learning aspects of Spark, but particularly focus on sort of like integrations with popular data science tools from like the PyData and R space. So a bit about me. I'm an Apache Spark committer working as a software engineer at Databricks, but my background is in machine learning. And my Berkeley connection is that I was here for a year, not in the AMP lab, but in wireless foundations. But yeah, before I go on, I first was hoping, since it's a bit informal, for a show of hands of people who have used MLlib before. Cool. Okay, and then a second show of hands for people who have used PyData tools or R tools. Cool. So quite a few people, but there will be hopefully something for everyone here. Gonna give a 1 or 2 minute intro of MLlib just to give a sense of what's there, but I won't spend most of the talk actually on MLlib itself. So our goal is to have pretty much a general machine learning library for big data, and that has a couple components. First, we want it to be scalable. You should be able to prototype on your laptop, but then run the same machine learning algorithm on a big cluster on much more data. And in this scaling, it should be robust, where a lot of that robustness, of course, we get sort of for free by being on top of Spark Core. We also aim to have coverage of common algorithms, and I'll give a list of those later. But the idea is that we want to be able to cover the majority of use cases, and then for the more specialized use cases, people can either extend or develop their own algorithms. We're also attempting to offer tools for practical workflows. Machine learning isn't just about running logistic regression. There are a lot of other elements in stringing together a practical pipeline, and we're trying to create functionality for that. And the final element, which this talk will be about, is integration with existing data science tools. Data science has been around for a long time, and there are some awesome tools out there. And so we're trying to think about how we can make it easy for people who are from those who are used to using those tools to start using MLlib without some huge gap in between. So in terms of algorithmic coverage in MLlib, here are the algorithms as of 1.5. You can't read them, of course, but let me summarize. At a high level, the set of learning tasks we try to tackle are classification, regression, recommendation, clustering, and frequent item sets, also known as association rules sometimes. But these are pretty standard sets of algorithms within each of these types of tasks. Logistic regression, linear regression, trees and ensembles, and so on. We also try to offer what I'll loosely call data utilities, everything from feature extraction and selection, which is an extremely important part of ML, to things like calculating statistics in a distributed manner, to both local and distributed linear algebra. And finally, I'll group things under workflow utilities. And this includes things like once you've learned a model, you want to be able to export it and import it later for future use, maybe on another system. We also have been working on what we're calling a pipelines API, which is essentially a higher level API for stringing together the many parts of feature extraction, model tuning, different algorithms, and so on in a practical workflow. And a big part of this is making use of the Dataframe's work, which Josh talked about earlier, and sort of writing on top of that work going on in Spark Core and Spark SQL, and using Dataframes as a very flexible data set representation for ML. And the final thing under workflow utilities is a lot of work can go into model tuning or hyperparameter tuning in machine learning. And one very common case of this is doing cross-validation. And so we try to prevent the user from having to write a lot of this rote code themselves and be able to just do plug-and-play model tuning. But what I really want to focus on is how Spark MLlib relates to existing ML libraries. And I'll focus on Scikit-Learn and R, largely because of their popularity. So Scikit-Learn is a Python toolkit which offers a very wide range of machine learning algorithms. And when I think of it, I think it's particularly notable because of its ease of use. You look at its homepage and it has like great documentation, examples, and so on. Very easy to get started. The other one I'll list is R, and I think what maybe comes to mind immediately for most people is like the immense number of packages, which they have, some 7,000. Things like GLMNet, which is like one of the most useful generalized linear method packages out there. So given these kind of toolkits, which are great libraries with documentation, guides, packages, extensions, there's been a lot of investment in these. And that means both in education and training, and of course in tooling and workflows, both in academia and in industry. The problem for a lot of people as big data comes along is that these are not traditionally developed for what I'd call the big data space. But of course now people are very excited about this. And the goal here is to do things such as, say, train a topic model on 4.5 million Wikipedia articles, or run recommendation algorithms using millions of songs and users and billions of ratings. And these are actual things which we've done with Spark. The other aspect people look for with big data is to be able to just throw more machines at a problem. Here's a plot looking at scaling with decision trees in Spark, where there are a number of workers on the x-axis and training time on the y-axis, so lower is better. And as you throw more workers at the problem, things just get faster. And of course, the point isn't just to handle a lot of data. The idea is that more data improves your performance in terms of accuracy or whatever metric on your problem. The other aspect of big data, I'd say, for machine learning is that you want to be able to scale gradually with your business. As you get more and more users, as you get more data sources, you want to be able to use the same workflows, reap those benefits without retooling. And the final element, I'd say, which I think is particularly felt by a lot of data scientists, is integration with production systems and being able to bridge this gap between the data analytics part and the production part. So how can we talk about bridging this gap? At school, I studied machine learning on a laptop, but now I want to do machine learning on a huge computing cluster. And so what I'll try to go through is how might you get from a single machine workload to a fully distributed one. And as I talk about that, I'll talk about the various integration points between the single and distributed machine workloads. So first, let's start with a wish list. First, I'd say you want to take your original code and be able to run it in a production environment. And in particular, for machine learning people, I feel like one confusing thing is being able to plug in and immediately use these distributed data sources. The next item in the wish list will be to be able to distribute your workload piece by piece. You don't want to have to do it all at once. Just do it as needed. And a big part of facilitating this will be easily switching between local and distributed settings with respect to your data and how you're running the computation. And the final item I'll list is being able to use familiar APIs. If you have a workflow, you want to have recognizable algorithms which you can switch to when you need to distribute things. You want to be able to have similar parameter settings so that you can, since you've done tuning in a single machine setting, you can take some of that knowledge to the distributed setting, and so on. And so to demonstrate this, what I'd like to talk about is a very simple task. So here's a chunk of data from a set of Amazon reviews. There are two columns. The first one is ratings from 1 to 5, 1 being bad, 5 being good. And the second column is the text of the reviews. People are reviewing these things they bought on Amazon, and they like them or they don't. So I'll call this sentiment analysis, where our goal will be, given text, we want to predict whether or not the person writing that text is happy or upset. And then the idea is, when you see new text, which may not even be a review, maybe it's a tweet about a product, you'll be able to apply this model and predict the sentiment. So let me describe the workflow, just to give you a sense of, especially if you're new to ML, the types of tasks you want to address in an ML workflow. So in this simple workflow, we'll start off with text and ratings. We're then going to pass it to a tokenizer. And the idea here is that we have this text, which machine learning algorithms don't necessarily know how to handle. So we're going to mush it into a nicer form. Tokenizer just means split it into words. So now we have a set of words. We next pass it to what I'll call a hashing term frequency module, which hashing refers to taking these words and hashing them to a fixed length numerical vector. And term frequency is just a text-based reweighting scheme. So what we've done here is taken our raw text and converted it to a nice numerical vector an ML algorithm will understand. And the actual algorithm we'll use is linear regression. And once we've trained that model, we'll be able to make predictions. Say on this text, we push it through our feature extraction, make a prediction using the linear regression model, and get some rating. And at the end, we can compare that prediction to the true prediction in our data. Cool, so these are sort of the three elements, and I'll lump them together into feature extraction and model training. Cool, so here's our very simplified ML workflow: feature extraction, model training. The other aspect of ML is model tuning. And here the idea is that these algorithms may have a number of parameters. Here I'm listing a regularization parameter, which essentially tells the model how much it should trust the input data. And the idea is that if it trusts it too much and overfits on it, then when you see new data, you'll make bad predictions. And so adjusting these kinds of parameters in ML algorithms can significantly change the performance. So to choose them, what we do is choose them in a data-specific way using what's called cross-validation. And basically, the idea is that you train a bunch of models, model 1, model 2, model 3, using different parameters, test them on held-out data, and then at the end, select your best model. Cool, so this describes our very high-level basic ML workflow. And what we're going to talk about first is how we can start distributing it. We'll start off just running everything on one machine. That's what I mean by the little red canister. But of course, you can immediately see one nice thing we could do, which would be, say, we're training a bunch of different models. Why can't we just train them in parallel? So we'll do that. We'll distribute the cross-validation, where each of these will train on a separate machine. So what I'd like to do is break out into a notebook and may need to do a bit of resizing, but all right, so what I'm doing here is showing a notebook, which this is a Databricks notebook, but all the code which I'm showing can be run just in open source. But this will be nice for the sake of describing this workflow. So we're starting off with a simple workflow, and it's going to be in Scikit-Learn. So I'm importing some stuff. I'm loading some data, and now let me look at this data. So this is the same data you saw before. Have a list of ratings, have a list of review text, and it's in a Pandas data frame. By the way, I'm running this on a 10-node cluster, but this code I'm running currently in Scikit-Learn and Pandas will be running on the driver. So we can look at this and say, okay, we have about 20,000 reviews, and we can take out the reviews and ratings in formats here, which will be nice to pass to Scikit-Learn. So our next goal will be to train a Scikit-Learn model. And now you don't really need to go through and understand each of these elements, but you can recognize the elements from the slides before. Hashing, the TF weighting, lasso, which is a type of linear regression. And in particular, at the bottom here, I'll highlight 3 possible parameters which we're going to tune using cross-validation. Okay, so we specify that workflow and the set of parameters to Scikit-Learn. And then what we need to do is run cross-validation. So Scikit-Learn provides this nice thing, grid search CV. And what this does is take the pipeline, parameters, a number of folds of cross-validation, and what it's going to do is, for 3 iterations, it's going to take some part of the data and leave out another part of the data. Then for each of our 3 parameters, it's going to train 3 models on this set of data and test on the held out set of data. And then at the end, it's going to find sort of the average results for each of the possible parameters and choose the best possible parameter. So in this case, it's learning 9 different models, took 27 seconds, and great. Now we have a model and can make predictions. So what I'm doing here is computing a score, and if you're familiar with it, it's the R-squared score. But basically, it's a score where lower is bad, higher is good, and in this case, we get 0.14. We can do things such as, say, evaluate on test data. Here I'm loading a new set of data and testing on it. And what you can see here is sort of our first integration, which I hid at the beginning of this workflow. If you notice, I'm loading this data from using a SQL context, and in particular from a Parquet format, which is like this nice distributed columnar storage. And then I'm using a Spark SQL method called toPandas, which just nicely converts this Spark data frame, which it loaded from Parquet, to a Pandas data frame. And then I can pass this directly to the Scikit-Learn model. Cool, so we see we got our squared score, 0.13, and so on. And of course, if we had more time, we'd train on more possible parameters, et cetera, and see about improving our predictions. The other integration I'd like to show here is the reverse direction, where, say we want to take our predictions and store them in a Pandas data frame, but we want to save them for some production users later down the line. And in order to do that, we can immediately convert that Pandas data frame to a Spark data frame and write it out to, say, a JSON file in, here it's a mounted S3 bucket. Cool, so I just did that. And what this demonstrated was largely conversions of data frames between Spark and Python Pandas. Cool, so if you recall though, what we were doing with model training was this cross-validation step, where we were training 9 different models. And of course, the natural thing we'd want to do is parallelize this. So let's do it. And what I'm going to demonstrate is a Spark package which we've been working on, which attempts to emulate Scikit-Learn's API very closely. So I'll go here to our imports, and the one thing which I will do is first, okay, sorry, I had forgotten to do this. I'll need to attach a library to this cluster. And once it is attached, I'll be able to import a grid search CV class with the same name, but, okay, cool. I think it's attached. So with the same name as the Scikit-Learn one, but which will essentially do the distributed computation and hide the difficulty of it under the hood. And for this, I'm essentially going to do exactly the same thing, except that at the end here, where I do the actual grid search cross-validation, I'll give it a Spark context so that it can distribute the computation. So what this is doing is same thing as before, 9 different tasks, but it's running them in parallel. And it'll be a tiny speed up here, but of course, as you scale this out, it'll be even more significant. So before it took 27 seconds, now it's 12, but you get the idea. Cool, so now what we have is this grid search object. And what it's going to offer, if I recall correctly, is an Scikit-Learn model. And so what I'll do, just so we can retain the rest of our workflow, is just extract that Scikit-Learn model from the grid search, and then we can do everything else as before. So we get the best estimator out of the Scikit-Learn model. We can compute, say, the score on our data, and so on. So what was this doing underneath? Well, the idea is that we're able to run Scikit-Learn jobs on workers in Spark and use Spark to coordinate those tasks. And I have more notebooks, which will be linked in these slides, but probably don't have time to go through them now, but I'd like to describe what they demonstrate. Basically, you can, as you scale up, you can start to hit other bottlenecks and start to distribute those. The next thing that the notebooks demonstrate is distributing feature extraction, where rather than doing everything on a single node for feature extraction, you may have a complex set of algorithms there and, say, want to split it up across different nodes. And what the notebook, which I won't have time to show, demonstrates is doing this distributed feature extraction using Spark, but analogous methods to the Scikit-Learn ones, collecting the results back to a Pandas data frame, and then doing what we just did using Scikit-Learn jobs in Spark workers and coordinating those via Spark to do this distributed cross-validation. Then finally, at the end, getting the Scikit-Learn model back. And then the final element, or notebook, will show completely distributed learning using just Spark, where we keep everything distributed, including training individual models. And this lets us scale up to even larger data sets. Cool, so I'll just quickly step through the wish list again. We had talked about running code on a production environment. And basically, all that was needed there in the case of Spark was being able to run Python code on the Spark driver. But what let us use those data sources were the Dataframe type conversions. We also talked about distributing the ML workload piece by piece. And we started with cross-validation, where there's this Spark package, which essentially just ran Scikit-Learn tasks on the workers, but had some nice API to hide that complication. We next distributed feature extraction, where the key thing there was converting between vectors and matrices between Spark and SciPy. And this is in one of the notebooks I didn't have time to show, but you could look at later. And then the final notebook, which again I didn't show, is just using Spark, where we finally distribute model training. So the final element in our wish list was using familiar APIs. And there, with a Spark package for Scikit-Learn integration, our main idea is to minimize modifications that the user needs to make to code. And with respect to MLlib, trying to have similar functionality and workflows as in other tools like Scikit-Learn. Cool. So I'll just quickly mention that some of the improvements we observed, if you go back and inspect some of the notebooks, are first faster model selection when you have a smaller data set. Then when you scale up to even larger data, faster training. And then finally, better predictions via that R-squared metric with more data. Those are in that final notebook. And in practice, you get even larger problems for many reasons. Use more folds of cross-validation, tune more parameters, and often you increase your model size or complexity as your data grows. So to repeat this at home, this demo is using Spark 1.5 and this PD Spark package, which will be released very soon. The demo notebooks will be linked from the talk slides. And I'll also mention there's another Scikit-Learn integration package, which takes a somewhat different tack, but again, is trying to make a familiar API, which can still leverage Spark. So you could check it out as well. So I've been focusing on the PyData space, but also want to mention integrations with R. First, I'll mention Dataframes, where, just like with Python Pandas, we have conversions between R local and Spark distributed data frames. And using Spark data frames from R, you can make SQL-like queries, as well as queries using familiar R-like APIs, such as this. Here it's saying, let's look at this data set. I think it's an Old Faithful data set, and look at the set of eruptions where the waiting time was less than 50. The other element of the R API is providing access to the distributed implementations of ML algorithms. And so currently, the only coverage we have are for linear models, like linear regression, logistic regression. But we're trying to follow an API very similar to what our users would expect. Here it's saying, let's model the sepal length of a flower by these other aspects, giving it a Spark data frame. And this is the same syntax you would expect from popular R packages. Cool. So finally, I'll just end with mentioning a bit about what's coming. So in 1.6, there are a number of new algorithms in MLlib. Survival analysis, online hypothesis testing, more feature transformers, faster clustering algorithm, and the ML Pipelines API, which is really cool and useful to a nice API to build complex pipelines. One of the final things which we're adding is persistence, where you can save and load pipelines. We're also providing more statistics for models and expanded API coverage there. There are also improvements to data frames with stats functions, R formula, and documentation. And the final thing I'll mention is, in terms of the roadmap, what we're really trying to focus on is completing out these APIs, providing more summaries and statistics expected by people coming from, say, R or other toolkits, and also ease of use, doing more things implicitly when possible, providing nice APIs like R formula, and improving documentation. Cool. And with that, I'd like to thank you.